Theorem 8. Compactness criteria. Criteria in Rn. Ну-ка там картиночку. Смотрите картинку-то. Вы посмотрите, что написано. Все же справа налево. Зеркал. Почему-то. Нормально? А раньше нормально все было. Раньше я себя видел по-нормальному, не в зеркальном отображении. Okay, I hope everything is okay. About covering and subcovering. We'll continue now with this covering and subcovering, so because that's about compactness again. So let K be a set in Rn. The following are equivalent. First, K is bounded and closed. Second, K is compact. Third, for arbitrary sequence x, m in K, which has a limit x naught, the point x naught should be in K. So if a sequence, oh sorry, I wrote closedness, sorry. For arbitrary sequence in Xn, sorry, that's wrong. There is a subsequence xmk, okay, from 1 up to infinity, which has a limit in K. That's it. Okay. Is it okay? Yeah, so it seems picture is okay. And I wonder, before it was completely very strange. What's about picture? Dear students on internet, is it okay? Okay. So. Но обычная картинка была здесь нормальная, не перевернутая. Странно. It's okay, everything is good. Okay, so. Okay, proof. Proof. So, we'll prove firstly from 1 to 2. So, I'll start with bounded. Okay, is bounded. Is bounded. What means bounded? Bounded means there is a ball which contains our set K inside. Our set K is inside our ball. So there is a huge ball which contains our set. But then we can find a cube which contains our ball. Because, yeah, so what can we do? We can just, so if K is a subset of a ball of radius r with center at A, then this ball is inside the cube. Which cube? I from 1 up to n, ai minus r. Okay, I'll include ai plus r. That is a cube which contains our ball. And this ball is compact. Any cube is compact. There was a theorem about it, right? There was a theorem which says that every cube is a compact set. So, cube is compact. And then, look what happens. K is closed subset of a compact set, cube. So, we suppose capital K is closed, and it is a subset of a cube, which is compact. And then there was a theorem which says if we have a closed subset of a compact set, then K is compact. And don't remember numbers of those theorems. That is theorem, and that is theorem from former lecture. Maybe I have numbers, but I'm not sure. 6 and 7. Most probably that is 7. That is 6. I'm not sure in numbers, I'm sorry. But you can find. Closed subset of a compact set is compact. Okay, so 1 implies 2. It is proved. Now let's prove implication from 2 to 3. And yeah, once again about covariance and subcovariance we'll see now. So we suppose K is compact. So capital K is compact. And I want to prove that there is such a property, property 3. So for arbitrary sequence, if we take arbitrary sequence of points of our capital K, there exists a subsequence which converges to a point in K. That's important. It's a kind of Bolzano-Weierstrass theorem, but with more precise indication of the limit. So, how we'll prove it? By contradiction. By contradiction. And what is contradiction? What is contradiction here? So suppose there exists a sequence that is a contradiction in capital K, which property it has? it has a property that, look, here we want to prove there exists a subsequence with limit in capital K, right? Now, I would like to suppose contrary, right? Right. What is contrary? So it means that arbitrary point of capital K cannot be a limit of a subsequence, right? So for arbitrary point x naught in K, x naught is not a limit of a subsequence. Of xm. Let us think what it means. What it means. Microphone is muted. Okay. Is not a limit of a subsequence. So what it means, not a limit of any subsequence? Look, let us think about it. So there is a point x naught, and we know that no subsequence has a limit at that point. What it means? It means that there is a neighborhood of our point such that how many points it has of our sequence. Look, if for arbitrary neighborhood there is a infinitely many points of our sequence, then there is a subsequence, right? So it should be only finitely many, right? And if there are finitely many points here, right, what can we do? We can find even smaller neighborhood, right? Here we have finitely many points, right? And what can we do? We can find smaller neighborhood which does not contain any point of xm, right? Except maybe for the point x naught itself, right? Because the point x naught itself may be among those points as well, right? We do not exclude it. So this property x naught is not a limit of a subsequence, means that hence there is a neighborhood let's say u r x too many indices may erase here x naught, because now for arbitrary x too many indices, I don't want to write so many indices. Okay, there is a neighborhood such that the intersection of our neighborhood with the sequence is contained in the set of the point x only. So you see, it might be empty or the point x itself, no other possibility, right? So once again, look, we take small neighborhood. If every neighborhood contains infinitely many points, then we can choose a subsequence which converges to that point, right? So every neighborhood contains infinitely many points, there is a subsequence which converges. This is not the case, right? Hence, only finitely many points. We can find a neighborhood which has only finitely many points of our sequence, right? If finitely many, then we can find smaller neighborhood which contains at most one point, maybe x or nothing, right? That is written here. That is written here, right? Now I'll use the definition of a compact set. So once again, about covering and subcovering. So look, what is going on now? For arbitrary point of our compact set capital K, right? I took arbitrary point here, x, right? And I found a neighborhood of that point with some property, doesn't matter, right? So there is a neighborhood around each point, x. Now, look at the union of all those neighborhoods. So, if I'll take the union of all those neighborhoods, what can we say about this union? So look, I have somewhere here I have our set capital K, right? Then what I do? I take arbitrary point, I find a neighborhood, right? That's it, like that. So for every point, its own neighborhood, many neighborhoods, right? As many neighborhoods as we have points, right? The same amount. Generally, compact may contain infinitely many points, right? So infinitely many neighborhoods also possible. Now look, every neighborhood of x contains the point x itself, right? For sure. If we have a neighborhood with center at x, right? Then it contains the point x. And we take union, right? So each point of capital K belongs to at least one neighborhood, right? So union of all those neighborhoods contains the set capital K. It means we have covering. So this means we have covering of K. This union covers the set capital K. So the set capital K is covered by the union of neighborhoods, right? Like here. Yeah? Then, and that is from the definition of the compact set. So what means compact? Capital K is compact. K is compact. Hence, there exists finite subcovering. So what is finite subcovering? So here we have, I don't know how many neighborhoods. A lot, right? Because it might be infinitely many points, right? But the definition of compactness says that we can choose finitely many. Okay? There is finitely many. What means finitely many? Finitely many points. Let's say x, how to number them? x1, so on, x capital N. These are points, right? Such that union now from 1 up to capital N of neighborhoods are x I of x I, right? Still covers capital K. That is finite subcovering. Finite subcovering. So, what it means, finite subcovering? Subcovering means what? those neighborhoods all together cover our capital K. Subcovering means we take not all of them, right? Only part of them. And they still cover. And finite subcovering means we have only finitely many. That's it. Clear? So that is finite subcovering. I hope I answered the first question which was asked. So now look. Remember main property of those neighborhoods. Recall. Look. Each neighborhood contains at most one point of our sequence, right? At most one. Now look. How many points of our sequence is in this union? At most one for each of them, right? So finitely many, right? So finitely many points of xm are in this union. And that is a contradiction, because our sequence has infinitely many terms, right? And it is in our capital K. That is a contradiction. That's it. Okay. So the last implication which we need, 3 to 1. Again, by contradiction. But here, we have to prove two assertions, in fact. One of them, capital K is bounded. Another, capital K is closed. We have two assertions. We need to prove both. So, firstly, let K be unbound. What it means, firstly, y is compact. Y is compact. 2 implies 3. So we suppose 2 is true and 2 is compact. Secondly, in the end, I did not understand what we exactly contradicted. Once again, every neighborhood contains at most one point of our sequence. Altogether, we have finitely many points, right? At most. Finitely many points of our sequence inside this unit, right? From the other side, all infinitely many points of our sequence should be in K. That is a contradiction. Infinitely many points should be here, but we know that at most one point in each of them, so at most finitely many. That is a contradiction. Okay, so let K be unbounded. What means unbounded? So, for arbitrary natural n, if we take, let's say, a neighborhood U n of 0, then it does not contain the whole capital K. So, look what I wrote. Unbounded means if we take arbitrary ball, right, it doesn't cover our set. Unbounded means it cannot be placed inside a fixed ball, right? Doesn't matter how huge you choose the ball, it doesn't cover the set, right? So there is a point of capital K. There is a point, let's say xn, which belongs to the intersection. Rn of x, Rn, I'm sorry, m Rn minus our neighborhood. So there is a point outside of our ball and still which belongs to our set capital K, right? So look, for arbitrary natural M, we have a point outside. It means that the distance from let's say, so xm is greater than m. That's it, right? Does not belong to the ball. Does not belong to the ball. Length of our vector is greater than m. Okay, then we have a sequence. We have a sequence in capital K, right? And by the supposition 3, look, for arbitrary sequence, there is a subsequence which has a limit in capital K. So there is a subsequence xmk which has a limit. Limit as k tends to infinity of xmk equals to x naught in, and it is in K. But if we have such a limit, then the limit of length also the same, right? And look here, every term is greater than mk. So this is a sequence of numbers which is unbounded. Unbounded sequence of numbers cannot have a limit, right? That is a contradiction. That is a contradiction. That means unboundedness is impossible. So capital K is bounded. And the last is, so last part of our contradiction is, so let capital K be not closed. What means not closed? Recall, closed means it contains every adherent point, right? Contains every means closed. Not closed means there exists an adherent point of capital K which does not belong to K. So once again, just definition of closedness. So closed means it contains all its adherent point. If it is not closed, then there is an adherent point which does not belong. Okay, so what means adherent point? Let me call it, let's say x naught, right? Adherent point, let it be x naught, right? So that is adherent point. What means adherent point? Adherent point means that the intersection with a neighborhood is not empty sorry, what I wrote, capital K. with this neighborhood is not empty for arbitrary r greater than 0. So what is at head endpoint? Intersection with arbitrary neighborhood is not empty, right? Now, look. It is written for arbitrary r. So, suppose r is 1, right? Then there is a point, let's say x1, which belongs to this intersection. Then r equals to 1/2. There is a point x2 which belongs to this intersection. And so on. So r equals to 1/m. Then there is a point which is denoted by xm, which is in this intersection. And so on. So we constructed a sequence of points xm, which is in our set capital K, and distance, so the length of this vector, is less than 1/m, right? So from this inequality follows that the limit of our sequence xm equals to x0. So the same is for arbitrary subsequence. xmk, arbitrary subsequence, also tends to the same x0, right? Arbitrary subsequence, for sure, right? Because if the whole sequence converges, then arbitrary subsequence converges to the same element, right? Now, look. What is written in 3? For arbitrary sequence, there is a subsequence such that the limit of this subsequence is a point which is in capital K. But we supposed that x0 does not belong to K, right? That is a contradiction. And theorem is proved completely. And let me make a couple of remarks related to this theorem. Remarks. First, the implication from 1 to 2 is called Heine-Borel theorem. In Rn. Second, implication from 2 to 1 and equivalence between 2 and 3 are relative. Sorry? Heine-Borel. There was a Heine-Borel theorem for real life that if a closed interval is covered by open intervals, then you can find finite subcovering. That is Heine-Borel for R. And that is Heine-Borel theorem for Rn. If the set is bounded and closed, then it is compact. That is. What is? No, it's new. Let me see. How is possible that a point being an adherent point and does not belong to the set? No, adherent point need not to be in the set. So the definition of adherent point is given. What is adherent point? Intersection of arbitrary neighborhood with our set is not empty. That is the definition of adherent point. Nothing else. It need not to be. So once again, recall the easiest case, interval 0, 1, right? In R1. 1 is adherent point. And it does not belong to our set. Okay. So let me return to remarks. So those assertions, look, from 2 to 1 and from 2 and 3 equivalent are valid in an arbitrary metric space. If you look at the proof, you will find that in fact, yeah, you see, of course, 0 appeared, but instead of 0, I could take arbitrary point. It doesn't matter. The main thing is just distances. So instead of 0, take arbitrary point, and here you have distance from that arbitrary point. That's it. So you don't need to change proofs even. Just replace length by distance, and that's all. So everything works for arbitrary metric space except for what? This. From 1 to 2. So this implication from 1 to 2 is valid only in Rn. That is important. And in fact, it is not true if you have infinitely many dimensions. Now, let us start new section. This will be section 3. Oh, I think I wrote section. Section 3. Section 3. Limits and continuity of functions and mappings. Or maybe not and mapping. So why I use both words functions or mappings? Because sometimes, so if we have f from Rn to R, then we say about function. But if we have from Rm to Rn, then we say about mapping. But I would like to say, of course, you can think about second case also as a function, it doesn't matter. But okay, it's about terminology more than about the essence of this notion. And before to give a definition of the limit, which is the main definition of this section, so I would like to give a couple more definitions of points. So definition. X naught is an isolated point of X, not X, let's see, of a set E in a metric space, once again, I'll start this section in general situation. I mean, functions or mappings are from one metric space to another. So from the beginning, all definitions will be given in a more general situation, metric space. Of a set in a metric space X, if X naught belongs to E and there is a neighborhood U epsilon of X naught such that the intersection of this neighborhood with E is only our point. And next definition, let me give using format. X naught is a limit point of E if it is an adherent point of E, but not an isolated point of E. So if we look at an example which I give in one of my first lectures in this semester, right? There was an example, let's say E example. Let me recall. Example. So E is, let's say, 1 union with 2, 3 intersected with Q, union with, okay, what is the rest? Let's say 4, 5. Let it be like that, right? So you see, adherent points, that is closure, right? Closure 1 together with 2, 3 together with 4, 5. So these are all adherent points, right? Now, which are isolated points? Isolated means one. Look at the definition. So there is a neighborhood which contains only that point, nothing else. So what are isolated points? Only one, right? One is an isolated point. All other points of the closure are limit points, right? Limit points. All other are limit points. Okay, now main definition. Let f be a mapping of a set D in a metric space X rho to a metric space, let's say YD. So distance in Y will be denoted by other letter D. And X naught be a limit point of D. Then limit as x tends to x naught, x in D, f of x equals to, let's say, L in Y means not means, just if and only if and only if and only if only if for arbitrary epsilon greater than 0 there exists delta greater than 0 such that for all x in D which satisfy to the inequality 0 less than distance between x and x naught less than delta, we have an equality distance between L and between f of x and L less than epsilon. That is called definition in the sense of Cauchy. That is Cauchy definition of the limit, right? And now definition Heine. So once again, same suppositions about let f so on x naught so on. So same supposition. Suppositions are the same, absolutely, right? This piece should be repeated. Suppositions are the same, right? Suppositions are the same. Then limit of f of x as x tends to x naught, x in D equals to L in Y if and only if, shortly if and only if, for arbitrary sequence, it is called also Heine sequence, xn in D minus x naught. Limit xn equals to x naught. For arbitrary such a sequence, we have limit f of xn equals to L. So these are two main definitions of a limit. If you substitute X is R and also Y, just usual real numbers, right? Then distances, what are distances? Modulus of difference, right? And then you recognize immediately definition of Cauchy and definition of Heine, right? Of a limit of a function. So we replaced modulus of difference by distance. That's all, nothing else. And then generality is essentially larger, right? Because metric spaces, they are essentially more general things. Sorry? Heine. Cauchy? Heine, yeah. Yeah. Heine. Both are definitions of limit of a function or mapping. So, theorem 1, definitions of Cauchy of limit by Cauchy and by Heine are equivalent. Proof. In fact, we repeat the proofs from the first semester if you analyze carefully, but replace modulus of difference by distance. That's all, nothing else. So first, let's say Cauchy to Heine, right? From Cauchy to Heine. So I suppose Cauchy definition is fulfilled. It is written here, right? Cauchy definition is fulfilled. Now, look, take arbitrary sequence which is written in the Heine definition. So take arbitrary sequence in D minus x naught such that the limit is equal to x naught. So what means this limit? We need to write down the definition of the limit, right? Definition of the limit says for arbitrary positive number, right? Now I would like to take as an arbitrary positive number just this delta, right? Look, firstly, we suppose Cauchy definition is fulfilled, right? It means that is true, right? So we take arbitrary epsilon, we can find delta, right? Now, I take that delta and substitute it into the definition of this limit. So for that delta, there exists number n such that for all n greater than capital N, we have distance from xn to x naught is less than delta. That is what I wrote from the definition, right? But also, we have extra condition. Look, xn, they do not coincide with x naught, right? So this distance cannot be 0. So I can put here greater than 0 because of that condition. Okay. So look, distance from xn to x naught satisfies those inequalities. Now look what is written here. Here it is written for arbitrary x in D. Oh, by the way, yeah, all xn are in D, right? For arbitrary x in D, which satisfies the same inequality as written here, right? What should be satisfied? So from Cauchy definition, right? What follows? Distance from f of this x, which is xn, to L is less than epsilon. Now, let me underline what we obtained, what is important for us. Look, for arbitrary epsilon greater than 0, right? Double underlined. There exists capital N such that for all n greater than capital N, we have distance less than epsilon. What is underlined twice is precisely that one. Limit f of xn equals to L, right? Because D is distance in second space. Why? Okay, so the first implication is proved. Now second implication, from Heine to Cauchy. From Heine to Cauchy. Okay. Here we proceed by contradiction. So what it means? What is contradiction? So we suppose that Heine definition is satisfied, but Cauchy definition is not satisfied, right? Cauchy is not satisfied. So that is not true. Let me write. That is not true what it means. There exists epsilon greater than 0 such that for arbitrary delta greater than 0, there exists x in D which satisfies the inequality distance from x to x naught less than delta, and such that distance from f of x to L is greater or equal than epsilon. So I took negation of this Cauchy definition, right? Carefully written negation. Okay, so here it is written once again for arbitrary delta, and we proceed as we did many times. So if it is written for arbitrary delta, then I put successively delta is 1, then delta is 1/2, and so on, right? So delta is 1. There exists x, let it be x1, which is in D. Distance from x1 to x naught is less than 1. Then delta is 1/2. There exists x2, I don't know this, the existence from distance from x2 to x naught is less than 1/2, and so on. Delta is 1/n. There exists x which is denoted by xn, 0 less distance from xn to x naught, less 1/n, and so on. We continue. So what we have? We have a sequence, right? We have a sequence xn, which is in D. Also, every time you see here distance is positive, it means xn cannot be equal to x naught. So all of them are in this difference, right? They are in D, but not coincide with x naught. And what we have? We have this, look at this inequality. Distance less than 1/n. Hence, as n tends to infinity, tends to 0, so distance tends to 0, right? So xn tends to x0. So look, all conditions of Heine definition are satisfied, right? We constructed a sequence in D minus x0 such that the limit of xn equals to x0, right? Then what? By Heine definition says that limit f of xn equals to L, right? Heine definition. But look at the last property of this negation of Cauchy, right? So I didn't write it here, let me write now. Distance from f of x1 and L greater or equal epsilon. Distance from f of x1, x2, sorry, L greater or equal epsilon. So for every point, we had this inequality, right? Distance from f of xn to L greater or equal than epsilon. Epsilon is fixed. This contradicts this limit, right? So the limit means that distance between f of xn and L should be as small as we want, right? But it cannot be according to those inequalities. So that contradiction finishes the proof. Okay. Now, let me firstly give some particular results for so look, now I would like to discuss a particular case. So consider now vector functions. What they are? It means f from R to Rn. So vector functions, sometimes they are denoted with this vector. No, just particular case. So I want to consider now properties of limits, but for two general cases, not very general. Firstly, we'll consider from R to Rn, then from Rn to R. Separately, two particular cases: vector functions and then functions of several variables. You see, they are similar, but it's better to consider them differently. So, or maybe instead of letter F, let me use A to divide, to separate those two cases, because second main case will be about those functions. So these are f and those a. So what they are? Let me write in more details. So look, a of t is value of that function from R to Rn, right? And that is a vector. So that is a vector. So a1 of t, so on, an of t, Now let's understand what are limits. Right? And maybe I'll write it like a lemma. like a lemma. Yeah. So lemma 1, lemma 1. Suppose T naught is a limit point of D in R, A from D to Rn, right? Then the following are equivalent. First, limit of A of t as t tends to t naught, t in D is equal to, let's say, vector L. Second, limit as t tends to t naught, t in D, length of A of t minus L equals to 0. And third, limit as t tends to t naught, t is in D, A I of t equals to L I from 1 up to n, where L vector is L1, so on Ln. So what's about proof? Look, the first and second, that is from the definition, let's say from Heine, because what is distance? Distance is just length, right? So what is written is precisely, look, this. Distance is model of length of difference, so that is precisely, let me recall what is it. So for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all t in D minus t naught, which, okay, in D, 0 less modulo t minus t naught less than delta, we have an equality modulo A of t minus L less than epsilon. And that is precisely same as we write for this. Limit of a function of a real variable. Here we have real variable now. Length is a real number. So if you write the limit, then this is precisely as here. Let me write it separately. A of t minus L less than epsilon, right? That is the last. Okay? So now what's about third? For the third, it's better to use not a Cauchy, but Heine definition. We know they are equivalent, right? In very general situation of arbitrary metric spaces. Of course, Rn and R are metric spaces. And remember that in Rn, so look, Heine definition. So I will write Heine definition. For arbitrary sequence Tn in D minus T naught, such that limit as n tends to infinity of Tn equals to T naught, right? The following is true. Limit as n tends to infinity a of Tn equals to L. That is Heine definition for that one, right? Heine definition is written. Look, Heine definition. That is precisely Heine definition, right? Now, look. We know that for a sequence, that is a sequence of vectors in Rn. Yeah, in Rn of n. N is not good. Let me put here m, 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 m. Yeah. Do not mix with dimension. Yeah. So these are vectors in Rm. According to criteria for convergence of vectors, we know vectors converge if and only if components converge. So limit as m tends to infinity a I of Tm equals to Li I from 1 up to n. This was criteria for convergence of a sequence of vectors. So sequence of vectors converges if and only if each components are convergent sequences. But now look what it means. If we look at this, these are Heine definitions for convergence of those functions, right? For those limits. These are precisely Heine definitions of limits of functions. So we obtain the desired result. Okay, so next important thing. So I have one lemma. Okay, and I have 5 minutes, right? Yeah, I can give the proof of next lemma, and so lemma 2 says if limit as t tends to t naught in d a of t equals to L, then the limit of length is also equals to the length of L. That is slightly different from what is written there, right? That is like continuity of length, I would say. Continuity of length. So, proof. Let me firstly write the definition of this. So, that is equivalent Cauchy definition. For arbitrary epsilon, there exists delta positive such that for all t in D which satisfy the inequality 0 less modulo t minus t naught less than delta, we have an equality length of a of t minus L less than epsilon. Now, we use the following form of triangle inequality. So greater or equal than this one. Why that is true? Why that is true? Because, look, for example, I can write like that. A of t minus L plus L no, it is not good. Plus L Oof. Yeah. Plus L, yeah. Length of this, right, is less or equal than length of A of t minus L plus L. That is triangle inequality, right? Look at what is written here. I can cancel L, right? And I have A of t here. So what it means? We have length of A of t minus L is greater or equal than A of t minus L, right? But then I can change here the order, right? I can change here the order and repeat. So what we obtain, that is equal to L minus A of t, which is greater or equal than L minus A of t. So look, we have one number which is greater or equal than difference of two numbers in both directions. It means that this number is greater or equal than modulus of the difference, right? Because it is greater or equal than both differences in both directions. And then what we obtain? So look, I can repeat now same sequence of quantos, and what we have? Modulo of this difference is less or equal than this, less than epsilon, right? And what is subtracted is precisely that one. And the proof is completed. So thanks for your attention. No more questions. Okay.